So what this problem is saying is that a bomb is launched vertically from the ground with a velocity of 30 meters per second. When it reaches the highest point of its trajectory, it explodes into two fragments which travel horizontally at 10 meters per second in opposite directions. What is the height at which this explosion occurs? And what is the velocity of the center of mass 1 second after the explosion? So what's happening here is that you have this bomb which is launched vertically with some initial velocity v naught equals, what was it, 30 meters per second? Yeah, 30 meters per second. And then it goes up to the highest point of its trajectory, and that is where it explodes. So it breaks up into, so you have, so this is the initial situation. Actually, it's not the initial. I'll just draw it like this. So it goes up to its highest point, and there, I'll just draw it all in one diagram. There it explodes. So this is my explosion. And then it breaks up into two pieces, and the pieces travel in opposite directions like this initially, right? So the question is, first question is, what height does that explosion occur? So that's nothing new about that part. You know how to find out how high something is going to rise when you know what velocity it was launched with. And then you have to find out where is the center of mass going to be 1 second after the explosion, right? Now, at first, you might think that this would be a hard problem to do because you need to know what velocities these two pieces have, because the piece on the left might be following some path like this. Piece on the right, let's say it has a higher velocity because it's lighter, it might be following a path like this. So then you need to figure out where these two pieces will be. Using projectile motion, you need to figure out where are these two pieces going to be 1 second later. And once you know the positions of these two pieces, then you can use the formula for the position of the center of mass to find where their center of mass is going to be, right? That's one way of doing it, and that will certainly work. But there's a far easier way of doing this problem, which is to recognize that the center of mass, the motion of the center of mass of the bomb, is completely unaffected by this explosion, right? Because the explosion is all internal forces, whereas the motion of the center of mass is only affected by external forces, right? And so what you can do is you can completely ignore the fact that the bomb exploded and just ask yourself, where would the bomb have been 1 second after it gets to its top, right? And that would be the answer. That's where the center of mass is going to be. Is everybody clear about the logic here? So that saves you a lot of work. So then it just becomes a chapter 2 kinematics problem, right? So we might as well just quickly do it. Suppose the bomb is launched with velocity v naught, right? How would I find out how high it rises? How would I find out the maximum height it goes up to? Bryce, do you want to help us with that?
You do the initial kinetic energy equals the final potential energy.
Absolutely. Yeah, absolutely. You could totally do that. Since we'll be using kinematics later on, we might as well just do this with kinematics, but that's certainly a better approach than kinematics. So we know that, let's say y equals 0 over here and y equals y max at the top. If you use this third kinematic equation, you know that velocity is 0 at the top, right? So if you use the third kinematic equation, 0 square is equal to v initial square plus 2 plus 2 times negative g times y final minus y initial. So that's going to be y max minus 0, right? And so from there you can solve for y max, and you'll get y max is equal to v0 square divided by 2g if you rearrange that, right? So that's how you can find the maximum height. Another way you could also find it is using the second kinematic equation and the first and the second kinematic equations. That would be exactly the same thing. So v final is equal to v initial minus gt, right? That's the first kinematic equation. And the second kinematic equation is y final equals y initial plus v initial t plus half gt square, or so it's minus half gt square, I mean. So what you could do is you could figure out how much time it's going to take to the top. So from the first kinematic equation, let's call this T max is the time. So from the first kinematic equation, you find that setting v equals 0, you get T max equals v0 over g, right? And if you plug that T max into the second kinematic equation, you'll get exactly the same answer that we got over here. Y max is equal to v0 squared over 2g. So all of this is old stuff. There's nothing new here at all, right? All right. Now, suppose I want to find out. So let's find the T max. So the T max is going to be 30 divided by 9.8. So can somebody tell me what is 30 divided by 9.8? 30 divided by 9.8, it's going to be very close to 3. 9.8 is 3.06. So that is the amount of time it's going to take to get to the top. And we want to know where it is 1 second after it gets to the top, right? So we can easily use this equation to find that. So y at 4.06, you would just plug in t equals 4.06 into this equation, and that would tell you where it is 1 second after it gets to the top. That makes sense? Everybody clear about that? And if you wanted to know what velocity the center of mass has 1 second after it explodes, you could just use this equation and plug in 4.06 instead of for t, because that's 1 second after the explosion happens. That clear to all of you? All right, so essentially, I mean, there's multiple ways of doing it. Like this kinematics method is not the only way. You could use other kinematic equations as well. But the point here is that it just reduces to a very simple kinematics problem. If you remember that the motion of the center of mass is completely unaffected by external forces, by internal forces. It's only affected by external forces.